Hi, welcome back to my channel. In abstract algebra, a field is an algebraic structure with the notions of addition, subtraction, multiplication and division satisfying certain axioms. The most commonly used fields which you are familiar with are the field of reals, the field of rationals and the field of complex numbers. And there are also some more fields, that is finite fields, fields of functions, PID fields and so on. The theory of field extension involves the roots of polynomials with coefficients in a field. This theory also leads to the impossibility proof for the classical problems of angle trisecond and squaring the circle with a compass and a straight edge. The theory of field extension also leads to the proof of the algebraic insolvability of quintic equation. In this session, we introduce basic notions to study general field extensions. For the completeness, we begin with the definitions of rings, ideals, ring homomorphisms, and some results without proof. So what is a ring? A ring is just a set where you can add, subtract and multiply. In some rings you can divide also, but in some rings you cannot. The ring at which you can divide, we call it as a field. What is the formal definition of a ring? A ring R is a set together with two binary operations, namely addition and multiplication, satisfying the axioms. Number one is the set R with the binary operation plus is a abelian group. Second is multiplication is associative, and third is distributive low holds in R. That means both left distributive and right distributive satisfies in R. That means A plus B into C is equal to A into C plus B into C, and A into B plus C is equal to A into B plus A into C. The elements of R may not have a multiplicative inverse, and the multiplication need not be commutative also. The ring is said to be commutative if the multiplication is commutative. That means A into B is equal to B into A for all A and B belongs to R. Now a ring is said to have a multiplicative identity or a unity if there exists an element 1R belongs to R such that A into 1 is equal to A, which is equal to 1 into A for all A belongs to R. So henceforth we denote A times B by AB, and 1 we use for 1R if we know the ring clearly. So now what is a unit? A unit is a invertible element. That means A is an element of R which is said to be a unit if it has a multiplicative inverse. That means there exists B belongs to R such that A into B is equal to 1 and B into A is also equal to 1. So in this case we can say that A is invertible or B is invertible, and the inverse of A is B and inverse of B is A. Can in a ring 0 is equal to 1? Yeah, the answer is yes. So in this case what will happen if I take any R belongs to that ring, then because 1 is the multiplicative identity, R is equal to 1 into R, but 1 and 0 are same, so you can write it as 0 into R, which is equal to 0. Therefore any element in R is 0 element. That means that the ring contains only one element, namely 0, and such ring we call it as a 0 ring. Now integral domain means a commutative ring in which every element or the commutative ring without a zero divisor. That means that if for any A and B in R such that AB is equal to 0, then either A is equal to 0 or B is equal to 0. Such elements A and B are called the non-zero divisor if A is not equal to 0 and B is not equal to 0. That means an integral domain is a commutative ring without zero divisors. So for example, if you consider the set of integers, in fact it is a ring and also it is an integral domain with respect to normal addition and multiplication of integers. So because you know that the product of any two integers is equal to 0 implies either one of the element is equal to 0, that means that Z is an integral domain. Z does not have any zero divisors. Now what are the units of Z? That means what are the elements for which it has a multiplicative inverse. So only 1 and minus 1 has multiplicative inverse in Z, and no other elements of Z has multiplicative inverse. That means the only units of Z are plus, minus, 1. Under ordinary addition and multiplication, the familiar number systems are rings. For example, the rings, the Q, the set of all rationals, the R, the set of all reals, and the C, the set of all complex numbers are rings with respect to the ordinary operations of addition and multiplication in that number system. Each of these rings are field. I mean, we are going to give a formal definition of the field later. So a few more examples. So consider the set of our polynomials whose coefficients are integers. In that set we denoted it as Zx. It is a commutative ring. And what are the units of Zx? They are precisely the unit of Z, and which is same as plus minus 1. And Z of x, the set of our polynomials, does not have any zero divisors. Therefore, Z of x is an integral domain. And if you take the polynomial ring or Q, which is a field, the set of our polynomials whose coefficients are rationals is a commutative ring again. And the units of Q are the units of Qx are the units of Q. Now, what are the units of Q? They are the non-zero elements of Q. And Q of x also does not have any zero divisors. That means Qx is an integral domain. Now, whenever you are considering some functions over a ring, we try to preserve the structure of the ring. Such a function we call it as a ring homomorphism. That means the ring homomorphism preserves the structure of the ring. In other words, it preserves the binary operations plus and multiplication. So the definition of the ring homomorphism is, if R and S are rings, then the ring homomorphism is a map phi from R to S satisfying phi of A plus B is equal to phi of A plus phi of B, and phi of AB is equal to phi of A into phi of B for all A and B belongs to R. If R and S has multiplicative identity, then phi of 1, the identity, multiplicative identity in R goes to multiplicative identity in S under this phi. So for example, let us take an integer A belongs to Z, and to define fa from the polynomial ring Zx over Z to Z defined as fa of p of x is equal to p of a. This is clearly, fa is clearly a ring homomorphism, and this map or the ring homomorphism we call it as evaluation map at A. A ring isomorphism means is a both bijective, both onto and injective, one and onto function and which is a ring homomorphism. That means an isomorphism means a ring homomorphism plus ring, it's a 1-1 map plus onto map. That means F from R to S is said to be a ring isomorphism if F is a ring homomorphism, F is 1-1 and F is onto. Now what do you mean by the kernel and image of a homomorphism? The kernel, suppose you have a ring homomorphism phi from R to S. Then the kernel of phi is a subset of R which is goes to 0 under phi. That means that kernel phi is equal to set of all R in R such that phi of R is equal to 0. In other words, kernel of phi is equal to phi inverse of 0. That means the inverse image of or the pre-image of 0 under phi. And the image of phi is defined as image of phi is equal to set of all phi of R where R in R, which is equal to phi of capital R. That means the set. That means each element, image of each element in R. So let F from R to S be a ring homomorphism. Then F is injective or 1-1 if and only if kernel of F is equal to 0. And F is surjetive if and only if image of F is equal to S. Now what do you mean by ideals in a ring? An ideal I in a commutative ring R is a subgroup of the group or the abelian group R plus that is closed under multiplication by elements of R. That means that whenever R is in R and A is in I, then RA belongs to I. So here I used the commutative ring because we need in the later part we need the two-sided ideal and that is same as the ideal of I. So and if it is not a commutative ring, the concepts of left ideal and right ideal comes into the picture. So to avoid that, I am assuming here as a commutative ring and my ideal is the two-sided ideal. For example, R itself is an ideal of R and 0, the singleton 0 is also an ideal of R. And that ideal we call it as a trivial ideal. If R is a commutative ring and A in R, then the subset RA, which is equal to set of all R times A for all R belongs to R, is an ideal of R. And that ideal we call it as a principal ideal generated by A and is denoted by angle bracketing. So another example is if you take any polynomial PH belongs to ZX or the polynomial ring ZX, then if you take all the multiples of P of X with the element of Z of X is an ideal and that is also a principal ideal generated by P of X. And if you take any ring homomorphism F from R to S where R and S are rings, then kernel of F is always an ideal of R. So what is a quotient ring? Suppose R is a commutative ring and I is an ideal of R. Then the set R mod I is equal to R plus I set of all cos X for R belongs to R. And this set R mod I is a ring under the addition and multiplication as S plus I plus T plus I is equal to S plus T plus I and S plus I into T plus I is equal to ST plus I, where S and T are in R. The ring R mod I is called the quotient ring. And the first isomorphism theorem of ring says that if F from R to S is a ring homomorphism, then the mapping R mod kernel F to F of R given by R plus kernel of F goes to F of R is an isomorphism. In other words, R mod kernel of F is isomorphic to F of R. Mainly we are considering with the later part, we are considering the prime ideals and the maximal ideal. The prime ideal is defined as follows. An ideal or a proper ideal P of a commutative ring R is called a prime ideal if For A and B in R with AB, the product AB belongs to P, then one of A or B belongs to P. That means A and B are in R with A into B is in P, then A is in P or B is in P. For example, PZ, where P is a prime ideal of Z, and singleton 0 is also a prime ideal of Z. And the ideal generated by h square plus 1 over z2 of h is not a prime ideal, because if you consider h plus 1 the whole square, that is equal to h square plus 2h plus 1, because 2 is a 0 in z2h, which means h square plus 2h plus 1 is equal to h square plus 1, and h square plus 1 belongs to the ideal generated by h square plus 1, but h plus 1 is not belongs to that ideal. Therefore, the ideal generated by h square plus 1 is not a prime ideal in Z2X. There is a characterization of integer domain. Suppose R is a commutative ring with unity and P is an ideal of R. Then R mod P, the quotient ring R mod P is an integer domain if and only if P is a prime ideal. Now we will come to the formal definition of a field. A field is a commutative ring R with an identity or a unity in which every non-zero element in R is a unit. That means that if A is an element of R which is non-zero, then you can always find an inverse, A inverse belongs to R, such that A inverse A is equal to 1 and which is equal to A into A inverse. A field is always an integer domain, and of course the field must contain at least two elements, namely 0 and 1. Therefore the smallest field is Z mod 2Z, which is contains only 0 and 1. Now what is a subfield of a field? So let F be a field and S be a subset of F. F is said to be a subfield of F if it inherits the structure of the field from that of on F. That means that with the binary operation plus and multiplication defined on F, S become a field. That means every non-zero element in S is a unit. Now what is the relationship between, what are the ideas of field? So the lemma states that a non-zero commutative ring R is a field if and only if it has no ideals other than 0 and R. That means that there is no proper ideal if R is a field. And if R is a ring with there is no proper ideal, then R is a field also. So let us see the proof of it. Suppose R is a field and I be a non-zero ideal in R. You take a non-zero element of I. Because A is an element of R and R is a field and A is non-zero, so A inverse exists in R. So A inverse is in R and A in I. Because I is an ideal, A inverse A belongs to I. That means 1 belongs to I. Therefore, for any R belongs to R you can write it as R into 1. And 1 is in R, 1 is in I and R is in R. Therefore, R into 1 belongs to I. Therefore, R belongs to I. Therefore, we get I is equal to R. Conversely, if R is a commutative ring with no proper non-zero ideals, then we show that R is a field. That means we want to show that every non-zero element is a unit. So let us take a non-zero element A. Consider the ideal generated by A. Because of the hypothesis, R does not have any proper ideal. That means the ideal generated by A has to be either 0 or R. But A is not equal to 0. Therefore, the ideal generated by A is not equal to singleton 0. Therefore, the ideal generated by A is equal to the full ring. Because 1 is in R, you can always find a B in R such that A into B is equal to 1. That means that A is a unit. Now, what do you mean by homomorphism of field? So it is just the homomorphism of a ring. So by this lemma, because we proved that any field has no proper ideals, because we found that if for a ring homomorphism, the kernel of f is an ideal. So if you have a field homomorphism, suppose f and f dash be two fields and f from f to f dash be a field homomorphism, then the kernel of f is an ideal of f, and that means that it has to be equal to either 0 or f. But if it is equal to f, then f is a 0 map. So but we are assumed that this is not a it is a non-zero homomorphism. Therefore kernel of f has to be equal to 0. Therefore that means that the field homomorphism, if it is a non-zero field homomorphism, then it is an injective map. So what is a maximal ideal? So let M be a proper ideal of a commutative ring R. M is said to be a maximal ideal if whenever I is an ideal of R with M is a subset of I subset of R, or M is contained in I which is contained in R, then either I is equal to M or I is equal to R. For example, the ideal generated by h square plus 1 or Rx is a maximal ideal. So there is a characterization of a field via maximal ideal. So let R be a commutative ring and M is a proper ideal of R. Then R mod M is a field if and only if M is a maximal ideal. Because we know that every field is an integral domain, and therefore by the characterization of integral domain and the field, we have every maximal ideal is a prime ideal. But not all prime ideals are maximal ideals. For example, if you take the zero ideal of Z, we have seen that 0 is a prime ideal, but it is not a maximal ideal. And another example is the ideal generated by H in the polynomial ring Zx is a prime ideal, but it is not a maximal ideal. Now, what is the characteristic of a field? The characteristic of a field is the smallest positive integer p such that p into 1 is equal to 0 if such a p exists, and if no such p exists, then we defined the characteristic of f as 0. The next lemma state that the characteristic of a field is always either 0 or a prime p. So if characteristic of f is equal to p, then for any a belongs to f, pa is same as 0. Pa means a plus a plus a plus a and p times. That is equal to 0. That means p into a is equal to 0 for all a belongs to f. So the proof, we have to prove that the characteristic of f is equal to either 0 or prime. So if characteristic of f is equal to 0, then we are done. Nothing to prove. Suppose characteristic of f is not equal to 0. So that means that there is some n, a positive integer n, such that n into 1 is equal to 0. We want to prove that this n is a prime number. Suppose n is not a prime number. Then n you can write it as a product of two smaller numbers. So let us say n is equal to r into s, where r and s are lies between 1 and n. So then, because of the definition, n is a characteristic of f, n into 1 is equal to 0, but n is equal to r into s, therefore r into s into 1 is equal to 0, which means that r into 1 into s into 1 is equal to 0. So, but f is an integral domain, the product of two things is 0 means what? One of them must be 0. Therefore, R into 1 is 0 or S into 1 is 0. But our choice of R and S are the numbers which lies between 1 and n. That means that a smaller number kills 1. That means R into 1 is equal to 0 for some smaller number than n, which is a contradiction to the definition of the characteristic of F field. So therefore, n has to be a prime number. So if A is in F, then we want to prove that P into A is equal to 0. So P into A means what? A plus A in P times, and which is using the distributive property. We can write it as A into 1 plus 1 plus 1, which is P times. So which is same as A into P into 1. But because P is the characteristic of F, P into 1 is 0. Therefore, which is same P into A is equal to A into 0, which is equal to 0. Therefore, we have proved that any characteristic of a field is either 0 or prime, and if P is the characteristic of F, then P into A is equal to 0 for all A belongs to F. Now let us define the prime subfield. Before that, the existence of prime subfield will prove. The theorem says that if F is a field of characteristic P, then F contains a subfield isomorphic to Z mod PZ. And if F is a field of characteristic 0, then F contains a subfield isomorphic to Q, the set of all rational numbers. Let us prove this. Let 1 be the unity of F. Consider the map F from Z to F given by F of K is equal to K into 1. This is a ring homomorphism. Therefore, by first isomorphism theorem of rings, we have Z mod kernel of F is isomorphic to F of Z. But F of Z is a subset of F. In fact, it is a subring of F, and F is a field. Therefore, F of Z must be an integer domain. Therefore, because F of Z is isomorphic to Z mod kernel of, Z mod kernel of is also an integer domain. But by the characterization of integer domain, we get kernel of F is a prime ideal. Now, what are the prime ideals of Z? They are either PZ or the ideal 0. So, kernel of F is equal to either 0 or PZ. So, when kernel of F is equal to 0, then F is injective. And in this case, we can think of Z as a subring of F. Because every non-zero element of F is invertible, we can get the element of the type P into Q inverse or P upon Q also belongs to F. For all P and Q belongs to Z with a Q not equal to 0. Therefore, we can think of Q as a subring of F and is the smallest subfield of F. So when kernel of F is equal to PZ, then we can see that Z mod PZ is a subring of F. Therefore, we prove that F contains a subfield isomorphic to either ZP, or in this case, if characteristic of F is equal to P, then F contains a subfield isomorphic to ZP and is the smallest subfield of F. That means that we have proved that if the characteristic of F is equal to 0, then F has a subfield which is isomorphic to Q, and if the characteristic of F is equal to P, then we have shown that F has a subfield isomorphic to ZP or Z mod PZ. So what is it? This field we call it as a prime subfield of F, and which is isomorphic to either Q if characteristic of F is equal to 0 or FP if characteristic of F is equal to P. By definition, the prime subfield is the subfield generated by the multiplicative identity of F. Note that if E is a subfield of F, then the characteristic of E and characteristic of F are same. Note that Z mod PZ has characteristic P and Q has a characteristic 0. Now we define the extension of a field. So if K is a field containing the field K, field F, That means F is a subfield of K. Then K is called the extension of F. And we denote it by K over F. In particular, every field is an extension of its prime subfield. Because we have seen that every field has a prime subfield. Either it is isomorphic to ZP or Q. So the field F in the extension K over F is called the base field of the extension. So if K over F is a field extension, that means F is a subfield of K. And because K is closed under multiplication, we can think of K as a vector space over F. Because K is closed under addition, and every element of F is an element of K, and K is closed under multiplication, so we can think of K as a vector space over F. And the degree of this extension is same as the dimension of K as a vector space over F. That means we are denoting the degree of the field extension by the angle bracket K colon F, and is defined as the dimension of K over F. In the next session, we discuss about a Kroneker's theorem. Thank you for learning with cell-based maths capsule. Thank you.